Talking more about polynomials today. It's we need to refresh ourselves what a polynomial even is. You can have polynomial expressions and polynomial equations, and we're talking about polynomials in one variable, versus polynomials with like xy's or xyz's, or just one variable involved. There's some basic rules to be a polynomial. It says you've got some very complicated thing for you to understand, where you've got a degree n in variable x. N is the biggest exponent that you see in there, or something like that. Like the degree of a polynomial, if it's in one variable, is the biggest exponent that you see. Okay, so like for example, if you look at this right here, which this isn't a polynomial, but isn't the biggest exponent that you see a 2, right? So that would be like degree 2 if it really was a polynomial, but that one's not. We'll understand why. But to be a polynomial, you have to have like n. N is your exponents right there. N represents a non-negative integer. A non-negative integer. Refresh my memory. What the heck's an integer again? Give me some examples of integers. 1, 2, 3, etc. Right? Those are actually natural numbers right there. What else classifies in the integer category? 0, right? Now these are all the whole numbers right here, and then -1, -2, -3, etc. But they say to be a polynomial, the exponents that you see have to be non-negative integers, aka whole numbers. You can have a 0, a 1, a 2, a 3, so no fractional ones, no negative ones, basically. Sound okay? So same thing down here, that the exponents have to be non-negative integers. Why is the following not a polynomial down here? Well, it's interesting. Is it in one variable? Yes. Isn't the only variables involved x, x, and x? Correct? That's in one variable. Cool. But why isn't it a polynomial? Exponent here, that's a non-negative integer. Correct? That's a non-negative integer. But see this? Where's that x located? Upstairs or downstairs? If I was to rewrite it with it upstairs, what would the exponent be if that was to change houses and come upstairs? Wouldn't it be a -1, right? So do you realize that this has a negative exponent on it? That's why it's not a polynomial. So in words, it's not a polynomial because of the term 5 over x. The exponent of x must be non-negative integer, and that should say 5x to the -1 right there. Here's something that we don't know much about at all. The next one of why it's not a polynomial. All in one variable, x and x. Cool. This is cool. No problem with that one. But see this, a lot of people don't understand what that is. If you think back to geometry, do you remember when you'd cube root something? Like when you were doing the volume and all that stuff, you needed to cube root. How did you punch that in your calculator? Like if you want to take the cube root of 27, how did you punch it in? 27 raised to the 1/3 power, like it's 1 over 3. This is a square root. So instead of the 1/3 power, what is that really right there? It's the 1/2 power. That's really what this says right there. Like the square root of x is really x to the 1/2 power. Now how come this doesn't work for it to be a polynomial? Because that's not an integer at all, right? That's a rational number right there. So it doesn't work. So it's not a polynomial because of the term. Why did this get all out of order? I don't know. Because of the term square root of 8, whatever. Because of this term, 8 square roots of x, because this is really the same thing as 8x to the 1/2 power, and you can't have that. Sound okay? So let's start with this bad boy. Down here, you got this on your practice sheet. It's all in one variable. This is a polynomial. It's called a constant polynomial because there's really no variables. What's the degree of it? Well, the degree is the biggest exponent that you see in this problem on x. Are there any x's even in this problem? It's kind of like this is saying 13x to the 0th power, because what's anything raised to the 0th power turn out to be? As a 1. So what's the degree of this puppy? What's the degree of this puppy? It's got degree 0, right? Because there wasn't any variables in there in the first place. Then they ask you what the leading coefficient is. Well, the leading coefficient is like the coefficient of the dude with the highest degree. Isn't it just plain old 13 in this situation? 13 is the only thing in this problem. That one is so easy that it's hard. It's like, ugh. Here, much better. Linear situation. Isn't that to the 1st power situation? It's all in x. What's the degree? 1. Now, what's the leading coefficient? It's the coefficient of the dude with the highest degree. See, this has degree 1, and this has degree 0, correct? We only care about this guy. What's the leading coefficient of it? 3. Is that all right with you? One more I'll do with you. Quadratic. Isn't the biggest exponent you see in it a 2? Right? What's the degree of a quadratic polynomial? 2. And the leading coefficient, there's 3 coefficients. There's a -5, there's a 3, and there's a -7. What's the leading coefficient? -5. Try the next one, the cubic one. And do you see how all of these are listed in what we call standard form? It's so weird, that standard form, you know. We kind of messed that up on our final. There's standard form of a linear equation. There's standard form of a quadratic. There's standard form of a polynomial. Standard form of a polynomial means it's written from highest degree to lowest degree. Doesn't it go 3rd degree, 2nd degree, 1st degree, 0th degree, right? That's in standard form because it's in order. If it's in one variable only, sometimes you'll have stuff with x's and y's, then you can't do that. This is the general form of what it looks like. What would be the degree of this? Well, this is x to the nth, this is x to the n minus 1, and that pattern continues. That means that these n's keep getting smaller and smaller and smaller, because aren't you subtracting from them? So what's the degree of this bad boy? Nth degree, right? It's just, in general case, it's this guy, it's the nth degree. What's its leading coefficient? A sub n is what that is. It's A sub n. A sub n. They're just saying that, like, the subscript is, if this is degree n, then this is the coefficient of the guy with degree n. Math language is pretty complicated to read. Those of you that go on to further mathematics, eventually they'll teach you how to read that stuff, but it's not for us to deal with now. Pretty simple. For 1 through 6, if necessary, rewrite the expression so that the powers of x are in decreasing order, which is called standard form. B, state the degree, and C, state the leading coefficient of each polynomial in one variable. But if the polynomial is an expression is not in one variable, explain why. It kind of means if it's not in one variable, you don't do any of the parts A, B, C. So let's look at number 1. Is that a polynomial in the first place? Yes or no? All the exponents are non-negative integers. Cool. Is it in one variable? Yes. So A, let's write it in standard form. What's the biggest exponent that you see? A 4, right? So negative 2x to the 4th, then plus x cubed plus 3x squared minus 7. That's standard form of this polynomial. Part B, state the degree. What's the degree of this puppy? So we'll please put the word degree in front of it. Degree 4. And then part C, state the leading coefficient. Leading coefficient. What's the leading coefficient? -2. And that leading coefficient thing seems so simple. It's like, why would you want to know that? It will tell us what the graph will end up looking like. We're just kind of setting us up for the next couple of pages. If you know the degree and you know what the leading coefficient, then you can tell what the graph of that polynomial will look like. Okay? Next one. Ooh, what do you think? What would we probably need to do first? Foil that out. Right? It's a binomial times a binomial. Let's foil it. Is it even a polynomial in the first place? Yes, and then in highest degree to lowest degree, it's pretty much there now, right, after I've combined my like terms and everything. What's the degree of this puppy? Degree 2. Now here's the question, just to kind of preview the next page. Do you know what the graph of this would look like? Yes or no? Do you know what the graph of this would look like if it's got degree 2? What would it be? It's a parabola. Part C, leading coefficient is 3. Do you know what this tells you about that parabola if the leading coefficient is a 3, as opposed to if it was like a -3 or something like that? What does the leading coefficient of 3 tell you? It opens up, right? It opens up. It's a parabola that opens up, right? Degree 2, leading coefficient is positive. Next. Whoops, my bad. Is that a polynomial on 3? Yes or no? Yep. Is it in one variable also? Yes. Put it in standard form. You don't have to put the placeholders or anything like that. We're not trying to do synthetic division or anything like that. There's some missing guys. We don't need them. From all the terms that are represented, we just put them in order. QL, degree of 8, leading coefficient of -4. Interesting question on the next one. First question, is it a polynomial? Yes or no? Polynomial. Yes, all the exponents are non-negative integers, correct? It is a polynomial. Is it in one variable? No. So we can't do anything with it. So we have to explain why it's not in one variable. Which term messes it up? Well, that's a variable. Which term messes it up? -3xy is the bad term. So let's put this. It's not a polynomial in one variable. Not a polynomial in one variable because the term -3xy. It's not a polynomial in one variable because the term -3xy has more than one variable. Next guy, you and Pal discuss. First, is it even a polynomial? Second, is it in one variable? If you say yes to that, what do you think? Is it a polynomial? Exponents, right? You're supposed to have non-negative integer exponents. Well, the way I look at it, that's a 3, that's a 2, that's a 1, and that's a 1, correct? But this is really what, since it's downstairs? If you bring it upstairs, it becomes a -1. So that's why it's not a polynomial. It's not a polynomial because of the term 4 over x. Right? That's the problem. Not a polynomial because of the term 4 over x. The exponent of x must be non-negative. And then in parentheses, I just kind of tell you, the reader, that that's really 4x to the -1. Like that 4 over x is the same thing as 4x to the -1. So it's not a polynomial because of the term 4 over x. The exponent of x must be non-negative. Then you can do 6 on your own. You can pause the video, give 6 a try. Next, fun with Euler's form. A polynomial function is a continuous function that is described by a polynomial equation in one variable. For example, this. Continuous means if you graphed it, like you'd get some cool shape or whatever, if you was to trace that with your pencil, you would never have to pick up your pencil. For example, remember the piecewise guys that we graphed sometimes? This is not continuous because don't I have to pick up my pencil to have to get over here to trace it, right? There's a gap in this thing. Polynomials are nice and continuous functions, and when you graph it, nice and smooth. Then, what do I want to say? The simplest polynomial function is in this. It's called a power function. So this is a 6th power function, this is a 5th power function, etc. Evaluate the functions at the indicated places with these particular functions. So they want us to find f of -5. That means we put -5 in for x into which function if they want f of -5. There's 3 functions provided here. Which one would we go into? F, right? Isn't this the f function? This is a g function. This is an h function. So let's do it. F of -5 equals. Everywhere you see an x, you should put parentheses around that and substitute -5 in. Parentheses make a huge difference. Good deal. Then think about your signs. You know, you can do a lot of this without a calculator if you have some stuff memorized. Think about your signs. If you take a negative number to an odd power, will it come out positive or negative? Negative. And if you take a negative number to an even power, won't it come out positive every single time? So Do we know what 5 cubed is right here? It's 125, but should it be positive or negative? Negative 125 plus 2 times negative 5 squared, which is really 25 or negative 25? 25. Then there's no exponents to deal with, so that's really just 50 plus 20, right? And I'm not opposed to you doing some stuff in your head, like if you figured out that was 25 and then took it times 2 right away and got this 50. That's all good in the neighborhood. We're that advanced now, we can do stuff like that. But I just like to show it for people that can't. Then when I get this far, I grab the old calculator and punch it in. I'm a fan of finishing what you're doing, right? I'm going to finish what I do and say f of negative 5 equals negative 5, and then put a negative 5 up there in the blank. Okay? Now let me tell you about the difference between students who will be successful for the rest of this chapter, like in logarithms and what we're going to do in the next chapter and all that stuff, versus those who don't. Those who are not that successful at things like logarithms and all that stuff, they take this green thing and type that in their calculator, and it will do it for you, right? Your calculator will do all of this for you. But if you can start practicing stuff like this, like taking 5 cubed and squaring stuff and realizing what's negative and what's positive, if you can start practicing that, then those other difficult things that you've heard nasty rumors about won't be that hard at all because you've been training yourself all along to deal with them. Cool? Next one. Which function are we going into? H. Wherever you see an x, put parentheses around it. Like I said, if we want to skip a little step, we can do that. We just got to follow the order of operations. If you screw this up by not following the order of operations, people would take negative 8 squared. You cannot do that. You have to take the negative 4 and square it first, right, and get 16. Then take that times 2 and get your 32. Exponents before multiplication kind of stuff. Those are pretty simple, right? Because you're just taking an integer and substituting it in for a variable. Pretty simple to do. Next one looks all messed up. Something looks funky about that. 5 times g of 2. What we need to do first is figure out what g of 2 is. So let's figure out what the g function evaluated at 2 is first. That 5 will come into play at the end. So we just need to figure out g of 2. Hopefully you get the g function evaluated at 2 to turn out to be 6, right? So if g of 2 is 6, what's 5 times g of 2? So it's 5 times g of 2 would be the same thing as if you substituted 6 into place. What's 5 times g of 2? 30. 6 times 5. We figured out what g of 2 was. G of 2 is 6, correct? Then you just do that times 5 at the end. Nice. F function. Now we're putting a fraction in, right? So let's do that on the old f function, f of a half. Put your calculator down. We won't need him. I have measured y'all's intelligence. Y'all are pretty darn bright. We can deal with these fractions without our calculator. We'll work together. All right, just get her substituted in. Is everyone cool with the substitution? Taking 1/2 and cubing it, first of all, what kind of number will you get, positive or negative? Positive. If you know what 1 cubed is and you know what 2 cubed is, you definitely know what 1/2 cubed is. What's 1 cubed? What's 2 cubed? So that will give you 1/8. You with me on that? Then we need to take plus 2 times 1/2 squared. What's 1/2 squared? 1/4. I don't try to do too much at one time. You know, I'm just whatever. If you can do that all at once, good for you, but I'm not gonna. Then negative 10 times 1/2. What's half of negative 10, my friends? Negative 5 plus 20. Nice. All I need to do then is just finish this little guy right here. So f of 1/2 equals 1/8 plus 2 times the 4th. Well, for those non-calculator people, it's 2 over 1 times 1 over 4, which is 2 over 4. What's 2 over 4? Really? 1/2. And I'm going to put plus 15. Where did plus 15 come from? Negative 5, 20. Awesome. Add them up. I need a common denominator. What would you want for a common denominator? 8. I would like 8 also. That's 1/8 already. Can you turn this into eighths for me very easily? What would you get? 1/2 is really 4/8. And then turning that into eighths, I need to take 15 times 8. 120 over 8. Is that cool with you? Yes or no? Now, add them all up. Real simple. It's over 8. All you got to do is add the numerators together. And how much do you get up there? Done. 125/8. Neato burrito. Again, only putting basically a monomial in. Interesting. 11. We will put a monomial in, but it's got a variable with it. If you take 3t and put it in for x, you will get t's in your answer, right? If you take a variable and put it in for another variable, it's not going to go away. So let's do that. F of 3t equals just wherever there's an x, you're going to put 3t in parentheses. And then we go back to the chapter 5 stuff that we did last semester. Doesn't 3t need to get cubed? And that's just a monomial in there. So everything's got to get cubed. It's like saying taking 3t times 3t times 3t. 3 cubed is, and t cubed is t cubed. Awesome. Try that with the next one. You could take 3t squared, figure that out, and just double it right away because you got to do the times 2. So what's 3t squared? 9t squared times 2? 18t squared. Right? And then the rest is pretty simple. Minus 30t plus 20. Then you look at it and see if there's any like terms you can combine or anything like that. Is there anything you can do to that? That's it. 27t cubed plus 18t squared minus 30t plus 20. Next one is you and Pal's job. Pause the video. Get that done for me, please. The simple things is when you put a monomial in. There's not really much work to do when you put a monomial. Sometimes you get variables, sometimes you don't. To the next page. I went ahead and did you the favor of showing you the functions. I don't like when those functions are on the previous page, you know. Pet peeve of mine. But here's the function still. We're doing the same thing now. We want the g function in number 13, correct? But what are we substituting in? Monomial, binomial, trinomial, what do we substitute? Binomial. That means it's going to get a little nasty if there's other variables involved, like if you got a square stuff or cube stuff or whatever. So just straight up sub in. The g function is x squared. So wherever there's an x, I'm putting a squared minus 1 in its place, right? Plus 3 times x, which would be 3 times a minus 1, minus 4. Is that handy dandy for you? Substituting it in. Then hopefully you have some of those tricks remembered. If not, you got to rewrite and FOIL out and all that stuff. But isn't this a binomial squared situation? If you'd like to not write that down every time, I'll be all right with that. This left half, if you just want to keep bringing the equal sign down, that's fine with me also. Okay? But we need a binomial squared. There's a trick to that. What's the trick? First move is square the first guy. So what's a squared squared? A to the fourth. Then the next move is twice the product of the guys in there. What is the product of these guys in here? Negative a squared, right? It's a negative 1 times a squared, right? So that's negative a squared, but I need twice that. What's a negative a squared times 2? Negative 2a squared. What's the last move? Square the last guy. First of all, what kind of number will you get every time on the last guy? Positive. The brain fart is people accidentally put 2. 1 squared is 1, right? So far, so good with that. We have done this. This guy, we do the distributive property on, correct? It's just a monomial times a binomial. So that would be plus 3a squared minus 3. Capiche? And then, of course, there's the minus 4 there also. Neato. Next move, finish it. Combine any like terms that could be combined and put it in standard form if it's in one variable, which this is in one variable. So highest degree to lowest degree. It's negative 3, negative 2, negative 6. Is that right? So then I got a to the fourth plus a squared minus the 6. Lovely. H. I'll let you substitute in. I got the formula up there for you. The function, I should say, up there. Yes, sirree. Substitution-wise, are we cool with that? Gets messy, right? Don't try to do too much at one time. In this term, there's some times 2-ing, and there's some squaring that needs to happen. What has to happen first? The square, right? You have to do all exponents before multiplication. So I'm going to bring this times 2 down, and I'm going to rewrite this binomial squared in parentheses still. So use the trick. See if you can get that binomial squared correctly. Square the first guy, twice the product, square the last guy. Then I'm just going to keep on moving to the right. Right, I'm going to do that times 2 later in the next step. Right? Don't try to do too much at one time. You'll make a bunch of mistakes. Square the first guy and you get 9c squared. The product of those is negative 12c. I need twice that. And then square the last guy and get a positive 16 plus 15c minus 20 plus 3. Yep. Now, I'll just keep on keeping on. I distribute the 2 to all of these. Then I bring my other stuff down. But since there were some like terms in my other stuff, that negative 20 and that 3, I just personally combined them together right away and got a negative 17. And then finally, 18c squared C's. I got a negative 48C and a 15C. I just kind of punch that in. If you could help me out there, what would that be? Negative 33C. Done with you, done with you. And 32 minus 17 is 15. Or excuse me, yeah, 15, right? One more. There's two more problems with these. I just want to do one of them. All right, let's get 15 done. Substitute into the g function, which I'll have up there for you. You can work with a pal if necessary. Should have got 25a squared minus 5a minus a 6. Good deal? Now, just for fun, what if this was a cubed instead of a squared? And you put this in there. How do you cube a binomial? Like if you wanted to take negative 4d plus 3 and cube it. How do you do that? I would do this. You see how I took it? Isn't it really 3 times in a row that you take it times itself? Well, can you do a trick first to take it times itself 2 times in a row? Then you'd have to take that result times this guy and la 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 la. Messy, 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 messy. Graphs of polynomial functions. It's time to realize that this is an important practice sheet to save. The graphs of some basic polynomial functions. First of all, it says the general shapes of the graphs of several polynomial functions show the maximum number of times a graph can intersect the x-axis. We are going to spend a lot of time talking about roots the rest of this chapter. The roots, or the zeros, are where the puppy crosses the x-axis at. Where does it cross the x-axis at? Well, you can tell how many times that graph will possibly maximum cross the x-axis by its degree. If you can recognize the degree of a polynomial, you know what's the most amount of times it will cross the x-axis. A degree 0 is a constant function. It's a horizontal line. Now, the dumb thing about it is this crosses the x-axis no times. What's its degree? 0. The dumb thing is this is an exception. If you had the line y equals 0, doesn't that cross the x-axis every time, right? So that's one small hiccup in the system. Other than that, it works every time. If you have a degree 1, isn't that like a nice, neat linear equation? How many times can a line cross the x-axis? It can only cross it once, right? It is not possible for a line to cross the x-axis in more than one spot. If you had a quadratic function, isn't its degree 2? What's the maximum number of times it could cross the x-axis at? 2. Now, isn't it possible for it to cross the x-axis a different amount of times, right? Haven't we seen it do it once, right? And haven't we seen it do it no times also, right? It's just about the maximum number of times it could cross the x-axis. Now, the cubic function has a degree of 3. It is possible for that graph to intersect the x-axis 3 times. It's also possible to go 2 times, 1 time, but it has to at least cross it once. It won't cross it negative amount or 0 times because notice the direction of this thing. Like we're going to talk about end behavior on the next page. Here's an odd degree, and notice the end, doesn't this one go up right here? Well, then that means this one has to go down. If you have an odd degree, one end goes one way, the other end goes the other direction, as opposed to an even degree. Notice an even degree, isn't 2 an even degree? Both ends go the same direction. Sound okay with that? Here's an even degree, degree 4. Kind of looks like a W, if you will. How many times did that cross the x-axis at? 4 times. That's the maximum. It doesn't have to cross it at 4 times, but it will not cross it more than 4 times in that situation. Notice the ends. Are they going the same way? Right? Even go the same way. Here's a 5th degree. It's an odd. Aren't the ends going in different direction? And this could maximum cross it 5 times. So to the backside we shall go. You will see that there's a little piece of paper taped over your worksheet because I didn't like how the original one was typed. There's two ways you could answer these questions. I didn't like the way our book did it, so I switched them around, is what we're doing. We're describing end behavior. So here's what it's all about. You don't have to write any of this stuff down. We'll kind of get there at the bottom of the worksheet, but I just want to explain this chart to you and how to read it. If you don't know how to read it, please ask questions. But first of all, talking about end behavior. Nobody cares about what's going on here in the middle. We care about the ends, and isn't that right meow and right meow? The end behavior of this situation. End behavior. So, if you have an even degree, and the leading coefficient is positive, for an example, you see f of x equals 5x squared. Isn't that degree 2, correct? And the leading coefficient is 5, which is a positive number. Hopefully you know that that's a parabola, and this makes it open up, correct? So let's describe its end behavior. Here's how we'll write it. I'll just kind of write it down instead of just reading it to you. You have to tell me as x, and we'll say this, approaches negative infinity. Right? As x approaches negative infinity, I've got some points here for you. See this green dot right here? What's the x value? Negative 1. What's the x value? What's the x value? Do you see how x is getting smaller and smaller and smaller, and it's approaching negative infinity? The x is approaching negative infinity. Because I could just keep going on forever and ever and ever. We'll follow that graph. What's happening to the y values as x approaches negative infinity? What's happening to it? Are they going up or going down? They're going, what's happening to the y values? 5, 20, 45. What's happening to the y values? They're going up, right? So as x gets smaller and smaller and smaller and smaller and smaller and smaller, it approaches negative infinity, right? Isn't that negative infinity? As x approaches negative infinity, tell me about y. Does y approach infinity or negative infinity? Y approaches infinity. So as x approaches negative infinity, comma, we don't say y, we say f of x. That's the same thing as y. F of x approaches infinity. Is that cool with you on that? Now that's one part of it. Part 2 is as x approaches infinity. So x could go this way also, right? As x gets bigger and 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 bigger, what happens to y? Doesn't it approach infinity also, right? So boom, f of x approaches infinity. This is the end behavior right here. What kind of degree was this, even or odd? Even. Did they approach the same place? Even have to go the same way, right? Don't they both point up, right? They point to positive infinity. So as x goes to negative infinity, like as you go this way, doesn't that thing go up? As you go this way, doesn't that thing go up? That's because the degree was even, and tell me about that leading coefficient. It was what kind of number? Positive. So what if it was negative, right? It's still an even degree, but what happens if that's negative? What would this quote-unquote graph do? Open up or open down? It would open down, right? So it would look like this. So this is an example. If f of x was negative 2x to the fourth, isn't that a fourth degree polynomial, which is even, correct? And what's the leading coefficient? Negative. That thing's going to open down. It kind of looks like a parabola, but it's not a parabola. It's a fourth power degree, and it's because nothing else happened to it is why it looks like a parabola. But as x approaches negative infinity, right? Doesn't that mean x has got to, as we go this way, right? As x comes this way, what happens to that thing? Does that approach infinity or negative infinity? This gets small, approaches negative infinity. And likewise over here, if x gets larger and larger and larger and larger and larger and larger, it means you're following it to the right. Where does this thing go? Up or down? Down to negative infinity. Cool? Those were even. They went the same way. Both of them approached negative infinity. Odd. Will they both go the same way? They go different ways. Snake. Odd degree. So this is 2x cubed, right here. F of x equals 2x cubed. Tell me what happens as x gets smaller. Here's x getting smaller, right? X is going to the left. My pen's going to the left. X is getting smaller. Where does that thing go? So as x approaches negative infinity, f of x approaches what? Negative infinity. Cool? Now, what happens when x gets larger? So X getting larger and larger and larger. Where's that thing goes? As x approaches infinity, f of x does what? Approaches infinity. Look at your f of x. Did they go different places? One went to negative infinity, one went to positive infinity. The other thing you have to memorize is where the snake is looking when you have a positive leading coefficient. The snake up this way, down that way, you know. When it's a negative coefficient, what happens is that snake switches around. It goes up this way and down that way. You have to remember that eventually. Okay, so as x approaches negative infinity, what happens to this thing? As x approaches negative infinity, f of x does what? Approaches infinity, and if x approaches positive infinity, f of x goes down, doesn't that approach negative infinity? Y'all? Let's see how we can do it. So, don't need to talk about that, already did. Draw a sketch to illustrate the 4 types of end behavior on this polynomial. Let me get you a straight edge. So, after you use the straight edge to make these 4 axes, what I want you to do is go back up in this chart, and here's type 1, type 2, type 3, type 4, so you can have a visual of what each one is supposed to look like. Type 1 is an even degree, and the leading coefficient is positive. Even degree, tell me about end behavior. Same both ways or different? Same, right? So even degree, you can think of that as like a parabola for now. Isn't that pretty cool? It's got to have a positive coefficient, so how will it open? Up or down? So just sketch me something that you feel is an even degree and has a positive coefficient. You could have done a parabola. I did a 4th power polynomial. I know it's even because tell me about my end behavior. Which way are they going? Same or different? Same. I know it's a positive leading coefficient because which way are they going? Up or down? Up. Cool. Try me a 4th power polynomial that's an even degree, but it's got a negative leading coefficient. See if you can sketch me a 4th power, guys. Instead of a quadratic, give me a 4th power. And the leading coefficient is negative. That means that they should point the same way, but go which way if it's got a negative leading coefficient? Down. So, too well? Even degrees go the same way. Leading coefficient tells you which way they point. Your parabola knowledge should really pay attention in there. Now the odd degrees, they're snaky, right? Kind of like a snake, if you will. If it's a positive leading coefficient, doesn't positive sound normal to you, correct? Think of this word, upright. Positive is upright. Positive is upright. So, where's that arrow going? To the left or to the right? To the right. Where is it also going? Up. Upright. If it's an odd power, odd degree, it's got a positive coefficient, this branch will go upright and the other branch will go the other direction. Right? It's kind of like a slithering snake. Positive coefficient means that as you go up, it'll go to the right. Right? Upright. So try the old negative coefficient. It'll be the complete opposite of that. You got to go different ways. Think this guy. Why doesn't that work? That would mean it would be an even degree because they're both going the same way, right? So, y'all good with that? Okay, positive, odd, upright. So, let's describe the end behavior. Here we'll do that on this one. As x approaches negative infinity is how it will always start out with. End behavior, tell me about x first. And I like to go from negative infinity to positive infinity. So as x approaches negative infinity, that means follow this. Like go to the left. Start going to the left. Isn't x, follow your graph all the way to the left, what happens to f of x? Does it go to infinity or does it go to negative infinity? So f of x approaches infinity. Right? As x itself gets smaller and smaller and smaller and smaller, y goes higher and higher and higher and higher. That's part one. You have to do the second part. As x approaches positive infinity, that means you'd be following your graph all the way to the right, 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 right. Now go to the end. What's happening in that thing? F of x does what? Approaches infinity again. Doesn't this thing still go up as you go to the right? Right? As you go to the right, nobody cares about this chunk. This part we don't care about because that's middle behavior. We want the end behavior. Isn't this near the end? As x gets bigger and bigger and bigger to the right, doesn't that thing go up? Cool? Please ask questions if you have them, because if you don't get end behavior, yes. What's part B ask us to do? Even degree or odd degree? You can tell by which way the arrows are pointing. Will this be an even degree or an odd degree? Even degree, because they're going the same way. Even degree. Sound awesome? The number of real zeros, I want to emphasize the word real because there will be some imaginary zeros sometimes. We'll find that out later this chapter. But the number of real zeros is where it crosses the x-axis at. Cool? Count them up. How many times does that graph cross the x-axis? 6. You with me on that? 6. Real zeros. Nice? Next one, let's describe the end behavior. It will always start as x approaches negative infinity, comma, we'll fill in that blank, and then the other one is as x approaches positive infinity, comma, fill in that blank. It'll always be the same generic setup. Cool? We just got to fill in those two blanks. So, as x approaches negative infinity, that means you take your deal near the end and you find the one going closest to the left, right? Where's that thing going? Up or down? Down. So that means f of x approaches what? Where's that thing approaching? Negative infinity. Cool? And how about as x gets larger and larger and larger and larger, as x approaches infinity, f of x approaches what? Negative infinity again. Did they go the same place or did they go to different places? Same place tells you what kind of polynomial it is, even or odd. That's an even degree. And now here's the mind blower. Notice the asterisk. Count the number of real zeros this has. How many do you count? 1. The answer is there are 2 of them, because this is what's called a double root. What? Do you remember back when we'd factor that and find the zeros? That's a binomial squared situation, and you'd get the same answer both times. You get roots of, say, -2, and you get -2 because it's x plus 2 times x plus 2 equals 0 is what it all factored into. Didn't you get the same root twice in that situation? How do you know when that happens? Is when you got a root and it didn't ever cross the x-axis in the first place. You see how this root, here it's above it, here it's below it. See how it crossed the x-axis? Here, I got a root because it touches the x-axis, but it never actually went across it. That means there's more than one root there. So, number of real roots, 1 with multiplicity 2. 1 with multiplicity of 2. There's one number there. That root is at -2, but it happened 2 different times. I know that is mind-boggling. Hang with me on it. We won't deal with that many, but there's multiplicity there because it's like a root that never crossed the x-axis, but it touched the x-axis. Okay with that? Next one. See if you can describe the end behavior. Let's see if I can, for those who are kind of struggling with filling the rest of this out, here's the gist. Every single time, it's going to look like that. If you do it in this order, this will be the same as x approaches negative infinity, f of x approaches blank. As x approaches infinity, f of x approaches blank. Okay? Here's how to fill in the blanks. This guy is the dude on the left. Up or down? Where's it going? Positive infinity or negative infinity? Up means positive infinity. Where's this one going? Down. What do we put there? Now, how come they went different ways? Because this is what kind of degree? Even or odd? Odd degree. Find the number of real zeros. Well, here's a 0, there's a 0, and there's a 0. Is there any multiplicity in those zeros? No, because they went from above or below or vice versa, right? So there's 3 real zeros. 2 with that.